All right, so we're good on the Pythagorean theorem, I assume, right? In our special or Pythagorean triples. That's just cartoon. Special right triangles, 45, 45, 90, 30, 60, 90. You learn this in geometry. There's relationships between the small sides and the hypotenuse small sides and long leg. You should be familiar with those. If you need to go back and take some time checking out some videos on that, feel free. Here's sine, and here's cosine, and here's tangent. You guys already learned SOHCAHTOA. I assume we don't need to go over SOHCAHTOA, but here's a fun little way to remember SOHCAHTOA. I didn't make these, but I'm amused by it. This is some old hippie came hopping through our apartment. His name's George, by the way. Anyways, SOHCAHTOA. Are we good on SOHCAHTOA? All right. SOHCAHTOA. So I don't know if you feel like you need to sketch this and write this down in your notes. Again, remember this is online. Probably you guys would be okay with this. Just pay attention for a moment. So that's theta right down there. And have you guys seen that theta symbol before and heard the word theta? It's a Greek letter. It's like a zero with a line through it. That's theta, and if we're talking about sine, the sine is the opposite over hypotenuse, so the side that would be across from theta divided by the hypotenuse, which you know is always the longest side, so 8 divided by 10, and then we reduce that to get 4/5. Cosine is adjacent over hypotenuse, that's the ka and SOHCAHTOA. Adjacent over hypotenuse, in this case, adjacent would be 6. That's the side that's next to, but not the hypotenuse. And then over the hypotenuse, so 6 over 10 gives us 3/5. For this triangle and that angle, tangent is going to be 8/6 or 4/3. Tangent is the opposite over the adjacent. And this should all be familiar from geometry. SOHCAHTOA. All right. Those are 3 of the trig functions. Do you know the other 3 trig functions? Say again?
Is it arc? Like sine?
There's the inverse trig functions as well, but no, I'm talking about the other non-inverse trig functions. No? Heard of secant? Or cosecant? Or cotangent? All right, well, we're going to learn about those today. Secant, cosecant, and cotangent. These are the reciprocal functions. So there are 6 trig functions that we're going to be worrying about. So introducing 3 new ones. Now the nice thing about these 3 new ones is that they're related to the original ones. The cosecant is the reciprocal of the sine function. The secant is the reciprocal of the cosine function. The cotangent is the reciprocal of the tangent function. Now, this is one of those situations where if I had been in charge when they invented this stuff, I probably would have done this differently. Would you agree? Doesn't it seem like sine should go with secant and cosine should go with cosecant? I feel like it would be easier to remember that way. But whoever decided, and maybe there's a really good reason for it. Actually, I've never really thought about why that is, but at any rate, that's not the way it is. Cosecant is the reciprocal of sine, secant is the reciprocal of cosine. The cotangent, tangent one, I don't have an issue remembering. We abbreviate these in the following manner. So cosecant is CSC. Cosecant is the reciprocal of sine. Secant we abbreviate as SEC. That's the reciprocal of cosine. And cotangent we abbreviate as COT, which is the reciprocal of the tangent function. So I'm writing these as 1 over. Now, oftentimes, sine, cosine, and tangent are fractions, right? Like we just did. The cosine of the angle was 3/5, right? So when we do the secant of the angle, we're just going to flip that fraction. It'll become 5/5. We'll do an example of that in just a second. Any questions about these? So this is one of the big new things for today for many of you is we've got 3 new trig functions to worry about. not too much important. You don't worry about writing this down. This is just a table for your 30, 60, 90 triangles, 45, 45, 90s. That's going to become much more important later on when we get into the unit circle. You guys good with Greek letters? Alpha, beta, gamma, theta? Have you seen those before? Gamma, when I write gamma, it doesn't look like so much like that as like a kind of a downward swimming fish. Same thing. Alpha, I generally write it kind of like this. It looks more like a fish than an egg. All right, so those are the main ones that we're going to see. Omega will come up from time to time as well. You guys know what omega looks like? Omega looks like that. It's kind of like a curvy W. All right. Actually, capital omega looks like. Seen that before?
Yes.
Okay. So, since sine is the opposite over the hypotenuse, and you don't need to write all of this down, I'm going to underline what I would write down if I were taking these notes. Sine is opposite over hypotenuse, and you probably don't even need to write that down because you already know it. But since sine is opposite over hypotenuse and cosecant is the reciprocal, that means cosecant must be the hypotenuse over the opposite. So we're going to go through and actually define what these things are in terms of the size of the triangle now. Cosecant is the hypotenuse over the opposite. Right, next up we are going to do cosine. And cosine is what? In terms of the sides, opposite, adjacent, and hypotenuse, cosine is adjacent over hypotenuse. So cosine is adjacent over hypotenuse. Secant is the reciprocal of that, so what's secant going to be? Flip it on its head, hypotenuse over adjacent. So cosine is adjacent over hypotenuse. Secant is hypotenuse over adjacent. All right, one more. Tangent is TOA. Tangent is
Opposite over
opposite over adjacent. Tangent's opposite over adjacent. Cotangent would be the flip that reciprocal, adjacent over opposite. So last one, tangent's opposite over adjacent. Cotangent is adjacent over opposite. Any questions so far? This isn't in here as a slide, but it's probably good to mention this right now because we're going to get into some stuff with it in just a minute. The tangent of an angle is equal to the sine of an angle over the cosine of that angle. Do you believe me? Yeah? No? If I started with this, let me start with this. Let me just take that. Okay, I'm going to start with this. The sine over the cosine equals, okay, what I'm going to do is I'm going to split this up. Now the sine is equal to what? In terms of the sides, that's what? Opposite over hypotenuse. And the cosine is equal to adjacent over hypotenuse. See how we're dividing by hypotenuse on both the top and the bottom of that fraction? Could we cancel those? Or you could think of it as, let's multiply by a fancy version of 1, hypotenuse over hypotenuse. Now, do you agree that we could cancel these? So sine over cosine is actually equal to, after we cancel that stuff, opposite over adjacent. What else do you know that's equal to opposite over adjacent? Tangent. That's one of our trig identities. We're going to be doing a lot of stuff with trig identities later on, I think in the second semester. That's where we will have the return of proofs. We'll be doing some proofs. Slightly different than the two-column proofs you did in geometry, but kind of the same. All right, let's look at an example with, well, it's the same triangle that we dealt with before. So in this case, if we were doing cosecant, it would be hypotenuse over opposite, 10 over 8, 5 over 4. Secant's hypotenuse over adjacent, which reduces to 5 over 3. Just have a look at this for a second. This is going to go away in about 10 seconds unless you guys have specific questions on it. So you really, if you go back to that same example that we did just a minute ago with the triangle, if you really want to get it down, the important thing is write down secant, cosecant, cotangent. Questions? All right, we spent a lot of time on the other three. Let's do an example where we go through and we find all 6 of our trig functions for a particular angle. So we're given a right triangle. You can go ahead and sketch that. We're given a right triangle that only has the right angle marked and then 2 of the sides. Is there sufficient information to figure out that third side? It's, what is it? 24? Did you do the Pythagorean theorem or you just knew that triple? You knew the triple? Good for you. This would be 24. Now, if you didn't know that, you could do the Pythagorean theorem, but the triples really save you a lot of time if you know. Sketch this triangle. I'm going to ask everybody to do this. We're going to write down 12 trig values for this triangle. 12 of them. I'll list the first 6, and you can start filling in what they are. I would like you to find the sine of A, the cosine of A, the tangent of A, the cosecant of A, the secant of A, and the cotangent of A. And when you're done with all that, go ahead and find all 6 of them for the angle B also. Go ahead and take a moment to do this. And keep in mind, once you've got the first 3, the last 3 are just going to be reciprocals. Just make sure you get them in the right places. So for this first 6, we're looking from the viewpoint of that angle here. For the second 6, we're going from B. Let me arrange these ones a little bit. What do you guys think of this new board? Pretty nice, there. Brighter. It's louder too, though. and check me on that if you're done already. I did rearrange that second column. But check that those answers are correct. And see if you can figure out why I rearranged them that way. So what happens when you switch from one angle to the other? What changes about your triangle when you switch from one angle to the other? Does hypotenuse change spots? No, it changes. Adjacent and opposite, they just flip-flop, right? So when you go from one angle to another, the adjacent and opposite just flip. Now think about what that's going to do to like sine and cosine. Sine has adjacent. Sorry, sine has opposite. Cosine has adjacent. If you flip adjacent and opposite, then you're just flipping from sine to cosine. Okay. So hopefully, you guys are able to see that I arranged these so that the values were exactly the same going across. The sine of A is 7 over 24, and so is the cosine of B. The cosine of A is 24 over 25, and so is the sine of B. The tangent of A and the cotangent of B are both 7 over 24. And the cosecant of A and the secant of B are the same. Okay? These things are called cofunctions. These pairs that I've created up here are called cofunctions. Cosine is the cofunction of sine. It's just like the version with the co up, right? Cosecant is the cofunction of secant. And it turns out when you're talking about those two angles, the cofunctions of those two angles are always going to be equal to one another. Yeah, there's actually a theorem for this. Tell me, in terms of measurement, what's special about these two angles? They always add up to 90 degrees. Can you give me a vocabulary word that means two angles that add up to 90 degrees? Supplementaries add up to 180 degrees. Complementary. All right, so the next theorem is called the cofunctions of complementary angles theorem. You ready for this? Cofunctions of complementary angles are, fill in the blank. Cofunctions of complementary angles are equal. They're equal. Cofunctions of complementary angles are equal. Always. Cofunctions of complementary angles are equal. Meaning if you've got two functions that are cofunctions and one of them has one angle and the other one has its complement, then the values of those two cofunctions are going to be equal. And there's some examples up here that kind of illustrate this. This is something that we're going to use when we get to our trig identities later on. We're writing our little, we call them trig identities. You guys will immediately identify them as proofs. How many of you guys enjoyed proofs? I think were you being facetious? Or did you really? Huh? I do too. Because they give you a starting point and then they give you the answer, and you just have to figure out how to get from point A to point B. Like, you know whether you got it right or wrong. It's very easy to know whether you got it right or wrong. It's just sometimes figuring it out can be a doozy.
That sucks is just remembering the names. I can remember what to do.
Yeah. What to call them. So the nice thing about when we do it in this class, we're not going to have to write out all the names of the properties and stuff. So we're just going to go. We're going to show step by step, very slowly, make sure that you can back it up with a theorem, but you don't have to know like the exact name of the theorem or anything. So that'll be better. So maybe it'll be more enjoyable for you this time around. All right, let's see if you get this. Let me give you a fill in the blank problem. Let's see, the cotangent of 20 is equal to, now give me a different trig function and a different angle. The tangent of 70, agreed? These two things are cofunctions. These two angles are complementary angles. Therefore, those two things have to be equal to one another. How about the sine of 15 equals the cosine of what? 75. You get the idea? All right. All right. Hey. These here are called the Pythagorean identities, and this is really getting a little bit ahead of ourselves, but we're going to be using this one with the 2 stars next to it. We're going to be using this so much that we might as well just introduce. It's going to be your best friend. Good old Pythagorean identity. There's actually 3 versions of it, but the one on the top is kind of the most important one. In fact, the one on the top is the only one you need to know, because you can very quickly derive the other 2 from the one on the top. Meaning there's one simple thing that you can do to that one on the top to create each of those ones below. Anybody know what you could do to the equation on the top to turn it into, for example, this one right now? What could you do? I'm not sure. Actually, no, that's probably the one we're doing. I might have told you wrong. Hang on a second. No, it's all good. It's written kind of in a weird format. How would I turn this one on the top into this one right here? Did you have an idea?
Like you switch cosine or cosine. Well,
No, we don't do any switching. It's one simple operation. Yeah, what do you think?
Because isn't like tangent equals
Yeah, the one we just talked about. Tangent was what over what?
is
Sine over cosine.
cosine, so then you like.
So here's what you do. Yeah, well, I'm sorry, I'm trying to steal your thunder. No, you tell me. What were you going to do?
No, I don't know.
You're not sure? Were you going to do this? Oops, no, I don't want to do that. Hang on. Back that up. How about this? Just divide through by cosine squared. No? Okay. It's all right. What's this? Sine over cosine is what? And cosine over cosine is, and 1 over cosine is secant. That's easy, right? If you know this one, divide through by cosine, you get this one. And if you divide through by sine, you'll get the other one. So the nice thing is, as long as you remember that sine squared plus cosine squared equals 1, you can always get the other 2. And these, again, you're going to use these lots, a whole bunch. All right, here's some quick examples. Why don't you guys, you don't need to write out every example if you don't want to, but at least think through these 4 examples, see if you can come up with some answers for me. I'll give you a moment to think about that on your own. Let me know if you have any questions at this point, if there's anything I can explain in more detail. Maybe jot down your answers so we can all compare. So the first three are that's that whole co-function of complementary angles thing. Maybe 35, 55? Tangent 60 would be the same as the cotangent of 30. Secant of 80 would be the same as the cosecant of 10. If you know the answer to the last one, it's a little bit of a challenge. It's equal to 1, correct. What? There was no cosine plus cosine equal 1. How? Can you explain it to us?
Sine squared of something plus cosine squared of something.
Okay, so you want to change this into a sine squared? You can do that. By the way, sine squared just means find the sine of that angle and square it, okay? What would the cosine squared of 25 be? It'd be equal to the sine squared of 65, right? Because those are co-functions. So if we switch to the co-function, we switch to the complementary angle. So sine squared of 65 plus cosine squared of 65, well, that is now the Pythagorean theorem, or for the Pythagorean identity. The sine squared of any angle plus the cosine squared of that same angle is always equal to 1. That's this guy right here. Sine squared of an angle plus cosine squared of an angle equals 1. So we kind of had to use both the theorem and the identity. Any questions there? Yes?
So it doesn't matter what the angles are inside of it?
It doesn't matter what the angles are as long as the two angles are the same. So if we're trying to use our Pythagorean identities, is that what you're asking about?
Yeah.
If we're trying to use our Pythagorean identities, then we must have the same angle inside of there. Now, a lot of times, it's just going to be a variable, but it would need to be the same variable. Mhm. Good question. Other questions? Okie dokie, let's solve some triangles. We already did this. Oh, here's a nice cartoon. Poor Bob. He's just a little too obtuse. All right, here's a triangle. We're going to solve it. Solving triangles, that's really what this whole unit's about. Well, not the whole thing. The vast majority of this unit's going to be about solving triangles. You're going to be given some information about a triangle. To solve a triangle means to find all of the missing pieces. So I'd like everybody to jot this down, whether it's just on scratch paper or in your notes. And we have 3 missing pieces to solve for, 2 sides and an angle. We're going to use our trigonometric powers to get it done. Now for this first problem, what would be the easiest one to solve for? I'd say B. Now, I guess easy is a relative thing, but I'd say B is going to be easy because we know that the 3 angles of a triangle have to add up to 180. So that means since this is 90, 35 and B must add up to 90. So 90 minus 35 is 55. So B is 55. That was easy. I thought so. Let's do A next. Now, we're going to set up a trig equation to solve for A. And we need 3 things for a trig equation. We need an angle and 2 sides. Which of those angles would you prefer to use? 35? I think that's probably a good idea. I'm fairly confident that I have 55, but just in case I made a mistake there, always smart to go with the given. Now I need 2 sides. I'm trying to solve for A. So I'm definitely going to use A. I wouldn't want to use C here because then I'm going to write an equation that has 2 variables and we can't solve it. So I'm going to use A, and I'm going to have to use the 8 here. So that is what 2 sides? Opposite, adjacent, hypotenuse. That's opposite and adjacent. Opposite and adjacent. Is that sine, cosine, or tangent? TOA is tangent. So we're going to write a tangent equation. The tangent of some angle equals a side over another side. The angle that we chose is 35. And our two sides were A and 8. And we want opposite over adjacent. So we're going to want the opposite on top, which is A, adjacent on the bottom, which is 8. And that gives us a nice equation that we can solve. Pretty easy one, too. We'll get rid of that 8 on the bottom by multiplying through by 8 on both sides. Get A equals 8 times the tangent of 35. Type that into our calculator. You guys can get your calculators out. Make sure you're in degree mode. Punch that in. Unless otherwise noted, we will be using 3 decimal places in this class. So please round to the nearest thousand. I don't have my calculator in front of me, so I'll rely on you guys. You got an answer? 5.602. Somebody confirm that? That's right. Excellent. Let's see if you can set up an equation to solve for C. Let's stick with the 35 again. So the equation's got C and 35 in it, and we've got a couple choices. We could use either the H or the 5.602. What's going to be the better of those two choices? 8, because what? Because it's an exact number. 5.602 is rounded. So exactly 5.602 was it. We don't want to use an imperfect number as part of the calculation, if we can avoid it. So C and 8, we got adjacent and hypotenuse. That seems like cosine to me. Does that sound right to you? Cosine 35 equals adjacent 8 or hypotenuse C, and there we go. Just remember how to get the C off the bottom of that. So there's this little shortcut where you can flip the C with the cosine 35. At this point, we should be comfortable with why that works. The reason that works, what we're really doing is we're multiplying by C on both sides. That allows us to cancel the C's down here. Now I've got C times the cosine of 35 equals 8. Now I need to get rid of the cosine. How am I going to get rid of that cosine? Divide on both sides by the cosine of 35. And we'll have C equals 8 over the cosine of 35. Sometimes this thing gets a little stuck. I wonder if the battery's dying. And we'll type that into our calculator and get an answer, and I'll trust you guys to do that. I want to move on to our last example of the day here. We're running pretty short on time. In this problem, we're just going to solve for A. So do a quick sketch here. For right now, anyways, we're just going to solve for A. So write me an equation that's got A in it. Note that you've got the opposite and adjacent sides. So would that be sine, cosine, or tangent? Tangent. Yep. Tangent it is. Opposite and adjacent would be tangent. Tangent of some angle is equal to some side over some side. What's the angle we're dealing with? A. There are variables on the inside now. Uh-oh. And tangent is opposite over adjacent. You guys remember how to get that A out of the tangent? We're going to do an inverse function. What we're going to do, and this may be different from how you were shown in the past, especially if you're in Algebra 3 last year. We're going to take the tangent inverse on both sides. That's really what you're doing when you do this. Because what does the tangent inverse do to a tangent? Cancels. Same way a square root and a square cancel each other out. Same way division by 2 and multiplication by 2 cancel each other out because they're inverses of one another. So we get A is equal to the inverse tangent of 7 over 4. We type that in our calculator and we get our answer. What questions do you guys have? Went through a lot of material today. This is 7.1. We're done with 7.1. We'll be moving on to 7.2 tomorrow. Please spend some time on 7.1 homework tonight. I'll take questions over 7.1's homework tomorrow. I don't want to get to the point where I'm only taking questions over homework the next day, but if that's what I need to do, to convince everybody to be working on the homework that night, then we're gonna have to start doing that. So please, I will take questions on 7.1 tomorrow, and I will take them the next day, but I'm probably gonna cut it off after that.
That worksheet notification.
Supposed to solve for the missing sign.
Like for the shading part.